So now we have two brief talks about the combination of direct imaging and astrometry, absolute astrometry. The first one is by Thayne Currie from UT. It's okay? No?
I don't think I understand how this works.
I don't know. It's
let me try again. So, where's end show at? Here. You just saw my talk. Okay. No.
You want to start from the beginning?
Yes.
Here.
Okay. Okay. What is forward? What is backward? And what is the?
This one's forward.
That one's forward. Okay.
And that's the laser pointer.
Okay.
Okay.
The big one. It's the big one.
All right. Okay, let's try this again. All right, thank you very much for giving me the opportunity to talk to you today about the OASIS survey to directly image extrasolar planets and brown dwarfs around accelerating stars. This is work that I am leading along with Masayuki Kuzuhara and a collaboration of about 30 researchers spread throughout the globe at different career stages. So as Emily said in her excellent talk, we're interested in increasing the efficiency of planet detections and learning more about them. So most of the planets we've discovered in the past 20 years have come from large or so-called unbiased or blind surveys, focusing on selecting targets based on properties like their mass and their age. Now these have been extremely important for establishing the demographics of superjovian companions and wide separations and getting information about their atmospheres, but they have some challenges. The primary one being that the low yield of new discoveries. So for example, the GPI survey, 2 new planets out of a parent sample of about 600 stars or so. Additionally, there are some challenges with exoplanet characterization just from direct imaging alone. So as was said in the previous talk, the masses you get from direct imaging alone are inferred masses from luminosity evolution models that try to map the brightness of a planet at a given age to its mass. But those are highly uncertain depending on the initial physics of formation, and they're also very susceptible to age underestimates or age uncertainties. Additionally, the typical time baseline for which you have direct imaging observations over a couple years is typically tiny compared to the orbital periods of a few decades to a century or so for directly imaged companions. So instead, what we want is an astrometry selected exoplanet direct imaging search. We use precision astrometry from the Hipparcos-Gaia catalog of accelerations to be able to identify those stars showing evidence for proper motion anomaly, a deviation from linear motion across the sky. And then we target those stars that are young enough to, in principle, have imageable companions. So this is done primarily with the Subaru telescope. Now, depending on what subfield you're in, you're probably most familiar with Subaru in terms of its capability to study planet formation. There's a poster on this by Erica Dykes. We also have, it's also famous for the Abiy protoplanet. We have more data for that. It's still there, and it's still very, very weird. But our focus is on fully formed planets. And so we use what is now the world's first 2-stage extreme-EO system, AO3K plus SCEXIO, to be able to carry out this science primarily. So AO3K does wavefront sensing in the near infrared with a pyramid wavefront sensor running about 1 kilohertz with a 3,000 actuator deformable mirror. So that's the first stage. The second stage is SCEXIO, 2,000 actuator deformable mirror running at 2 kilohertz doing wavefront sensing in the optical. So a lot of mirror segments. Right? It's able to achieve contrast at about 10⁻⁶, wide separation in 10⁻⁵, very, very close to the star. And we're able to get spatially resolved spectroscopy all the way from 1.1 to 2.4 microns with the Keras integral field spectrograph. Now these data are complemented by thermal infrared imaging with Keck, and our primary allocation is about 42 nights at time. We have additional allocations at time we've got through competitive proposals. We forecast over the course of a couple of years this may exceed over 65 nights of time. And so what we try to do is we try to focus on those systems that have a proper motion acceleration plausibly caused by a substellar companion, possibly a planet. And so that's the plot that you're seeing on the right is showing this histogram distribution of minimum masses. We're following the analysis from Pierre Cavella to be able to determine this. So primarily we're probing systems that can plausibly be caused by acceleration due to a 5 to 15 Jupiter mass companion. So our first discovery is this thing, HIP 54515b, aka 66 Leo. So if you plot this on an HR diagram, this lies very, very close to Beta Pictoris. right along the Pleiades sequence. This is a very young star. But if you look through archives, this has never been observed with GPI, Sphere, Keck, anything. This has never been targeted for an exoplanet search. This is some rando young A star. But it shows a very strong proper motion acceleration. So we targeted it, and we have a detection. Right? It's very, very close to the star, about 3 to 4 lambda over d. So this is our first discovery, and it was co-led by Yi-Ting Li, who's an amazing postdoc at University of Michigan. And also on the personal note, we dedicate this work to my friend Uncle Wally, who's a colleague in Hawaii. So if we look at the spectrum of this object, this appears to be something on the order of something between the M to L transition object. If we jointly model the relative astrometry we get from Currie with the absolute astrometry we get from Hipparcos and Gaia, we're able to constrain the mass to about 17 Jupiter masses, a mass ratio of a little bit less than 1%, and a semi-major axis of 25 AU and about 0.4 for the eccentricity. Now, I know this is maybe a little bit of a charged slide, but I'm just going to nip this point in the bud. Most of the posterior distribution for this object lies above 13 Jupiter masses. But to be very clear, we think the evidence for this object being a planet is favored over that being a brown dwarf. The primary reason is that if you look at the established recent peer-reviewed literature, not what some person said in the 1990s, the deuterium burning limit fails to distinguish between planets and brown dwarfs. Just repeat that again. Fails to distinguish between planets and brown dwarfs. This is also supported through independent work. What we did in this paper was use a new sample of companions from astrometry and rate of velocity with dynamical masses to be able to reconsider this issue. And so HIP 4515b lies below this turnover in mass and also below this turnover in mass ratio, dividing planets and brown dwarfs. Our second discovery is led by my postdoc Mona El-Morsi, who's an excellent instrument scientist, technologist, and also does amazing science. This is 71618b. This is a likely 60 Jupiter mass brown dwarf on an 11 AU eccentric orbit. The interesting thing with this one is that yes, another discovery, but it also just happens to be located in a region interesting for the Roman chronographic instrument technology demonstration. If we take either empirical benchmarks or atmosphere models and predict its 575 nanometer contrast, we get a value of a few times 10 by 7. This is a very bright star, near vetted PSF reference stars. A high signal noise detection of this object with the Roman chronograph would single-handedly fulfill TTR5. So we have additional discoveries, and so one of these is presented a poster by Yi-Ting Gu. So the original 4 discoveries, the latter 2, were named after the Beatles. We have to use a different naming system. So we have a couple systems that, they're interesting, but probably more for stellar astronomers. Well, they're there. We'll call them archers. So we have others that were definitely brown dwarfs, but there is so moderate contrast, we probably don't think they're near the turnover between planets and brown dwarfs. But we're getting warmer, pikes. A lot of the first accelerating star discoveries are LT transition objects for some reason. This mold that we established for some of our first discoveries. Unfortunately, our next object, while being one of those, the star is not very well characterized, but hopefully we'll make it so well characterized. Our final object is a very, very cool companion. In fact, if you look at the spectrum, scroll from short to long wavelengths, it sort of like pulses invisible, visible, depending on whether or not you're looking in and out of the methane absorption. Just like the Bajoran wormhole, or the words Cisco. Who do you have left? Unfortunately, I ran out of time for my talk preparations. I'm sorry about that. So what do we learn from this? So the major scientific impact, I think, is being able to better characterize the evolution of planetary systems. We're able to add more systems with dynamical masses. So this is just showing the literature objects plus our published or well-constrained sample. If we sort of forecast what we think we'll be able to do, we'll be able to at least double the number of systems with dynamical masses younger than a gigayear. And then we can study in a little bit more detail their atmospheric properties. So for example, as my graduate student Danielle Bovey showed, we can study, for example, how the H-band feature sensitive to surface gravity varies as a function of time. Another thing we can study is eccentricities. This is an advance first made by Brendan Bowler. So we have some very low eccentricity objects at low masses. At very high masses, well into the brown dwarf regime, these tend to have very wide range of eccentricities. Hopefully, we'll be able to constrain this sort of transition point in better detail. Once you have a new discovery, the bat signal goes out. You should follow it up with everything. And so this is a really interesting poster and a recently accepted work showing the follow-up of HIP 9977b, where they argue that this shows evidence for enhanced metallicity and thus a planet-like formation. So even though it's massive, walks like a duck, quacks like a duck, it's probably a duck. And the other advantage of this work is that it enhances the science and technological return for NASA missions. So I already mentioned how it aids NASA with the Roma Space Telescope technology demonstration, but even for additional tests, it can be very, very, very useful. So for example, 54515b is a good test of CGI's performance in the low stellar flux small angular separation limit. So what do we do next? Well, I think this kind of program is going to be made far more powerful, not just by Gaia DR4, but by technology advances and by coupling our data with precision radial velocity that was just mentioned in the previous talk. So if you look within that semicircular region, that contrast is about on the order of 2 times 10 to the minus 6. This is without PSF subtraction techniques. So our performance could get substantially better in the future, especially if we're able to convince Subaru to keep spiders on the telescope. And a poster by my graduate student, Jay Lee, couples accelerations with now a colossal amount of archival RV data available. He's already discovered over 25 new planets, some of which are potential Roman CGI targets where we know exactly where to look. So that kind of gives you an overview of the survey. We have a new planet, a new brown dwarf. We're finding more. It will hopefully provide insights in the formation and evolution of planetary systems and enhance the scientific return of NASA missions. So thank you very much for listening. I'll take any questions you have.
Questions? Okay, I can ask one. I guess you plan to make a statistical survey, get statistical results. Do you have, even if you, well, you can be optimistic, do you have any numbers to give?
So we have some ideas of statistics. The first is trying to characterize our detection rate compared to unbiased surveys. So the current estimate right now is that we're running about 4 to 5 times higher in terms of the detection frequency compared to unbiased surveys. The other thing we can do is sort of estimate the overall detection rates. So like how many of these systems have planets, but they're just hiding. And so a 30 to 40 meter class telescope might detect them. So we're interested in that. And we're also interested in statistics in terms of how to anchor luminosity evolution models. And so that's something we'll get to at some point.
Thanks for the nice talk, Thayne. Beautiful results so far. Max Miller-Blancher, UCSB. I'm curious as to, it seems like there are a lot of nights. Is it structured so that you do have time kind of pushed back for when Gaia DR4 is released, or how much time do you have left? Like, what's the overall structure like?
Sure. So our primary allocation goes through about January 2027. We didn't intentionally try to push back our time allocation for Gaia DR4s, mostly driven by the fact that we're asking for a lot of time on Subaru, and as you well know, sometimes that just means 1 or 2 people supporting. So Olivier was by himself for a lot of Christmas break supporting Skexio from the mountain, and that was probably very lonely, and we don't want to make life hard for him.
No more questions, so thanks again, Thayne.